Chapter 20, problem number 20. Determine the work done by 5 moles of an ideal gas that is kept at 1,000 degrees C in an expansion from 1 liter to 5 liters. Okay, well let's take a look at this. We have an ideal gas, so we know that from the ideal gas law, PV equals nRT. And then we're asked to find the work done by 5 moles of an ideal gas at 1,000 degrees centigrade. So, I'm sorry, 100 degrees centigrade. So that means we're going to stay at a constant temperature. So it's going to be isothermal. And we know that the work done should equal a negative pressure times a change in volume. So we can write this as negative pressure from this, which would be P equals nRT divided by volume. So this would be negative nRT divided by volume dV, integrated from initial volume to final volume. This would be a negative nRT, natural log of the volume from initial to final, which would be a negative nRT, natural log of V final over V initial. This would be log of V final minus log of V initial, which would be log of V final over V initial, which I could write, since it's negative out front, as nRT, natural log of V initial over V final. That, for an isothermal expansion, is the work done in general. So you probably could have just started from this formula right away. But I just wanted to show it on this first example that we're using this. So, we want to find that work done. Now that would be the work on this, work by the system. So we have work by the system will equal nRT V final, natural log of V final over V initial. We have 5 moles. Our gas constant is 8.31. Our temperature is 100 degrees C. We want that in Kelvin, so that will be 373.15 degrees Kelvin. Natural log. And the volume is given in terms of liters, and we're going to have liters over liters, so the units of the volume will cancel out. So the fact that we go from 1 liter to 5 liters will just be a ratio of 5 over 1, and that will be unitless inside that natural log. And when I calculate all this out, I get 2.5 times 10 to the 4. 2.5 times 10 to the 4 joules. So that would be the work done by the gas, a positive amount of work. The work done on the gas would be the negative of this. Problem number 21. 5 moles of an ideal gas expands isothermally at 100 degrees centigrade to 5 times its initial volume. Find the heat flow into the system. Well, this is actually the same problem, but instead of asking for the work done by the system, they're asking for the heat flow into the system. So what we would say is, from the first law of thermodynamics, we could say that the change in internal energy is equal to the heat flow into the system plus the work done on the system. But since it's isothermal, the change in internal energy is 0, because the internal energy is proportional to the temperature. So if the temperature doesn't change, your change in internal energy will be or your internal energy will be constant, so your change will be 0. So this is 0. So the heat flow will equal a negative of the work done on the system. And for that matter, it will be equal to the work done by the system. And this was the work done by the system. So our heat flow into this system will just be 2.5 times 10 to the 4 joules. Problem number 22. An 8,000 kilogram aluminum flagpole, 100 meters long, is heated by the sun from a temperature of 10 degrees Celsius to 20 degrees Celsius. Find the work done in joules by the aluminum if the linear expansion coefficient is 24 times 10 to the minus 6 per degree Celsius, and the density of aluminum is 2.7 times 10 to the 3 kilograms per cubic meter, and 1 atmosphere equals 1 times 10 to the 5 newtons per meter squared. Well, let's take a look at this flagpole for a moment. Problem number 22. So we have a flagpole, and we're told that it's 100 meters long. And the mass is 8,000 kilograms. We're going to have a temperature change from 10 degrees Celsius to 20 degrees Celsius. So our change in temperature, which would be T final minus T initial, would be 20 minus 10, or 10 degrees Celsius. And we're given a couple of other information data. We're told that the linear expansion coefficient for aluminum, which would be alpha, is 24 times 10 to the minus 6 per degree Celsius. The density of aluminum is 2.7 times 10 to the 3 kilograms per meter cubed. And we're told that 1 atmosphere, we'll go a little bit more accurate on this one, is 1.013 times 10 to the 5 pascals, newtons per meter squared. Now what we'd like to do is find the work done. Now to find the work done, we basically need to find this. If we're going to do this all at 1 atmosphere pressure, then the thing that is changing is the volume. The pressure is going to remain constant, so work will be the constant pressure times the change in volume, isobarically in a sense. So we need to find the change in volume of this flagpole. Now we're heating the flagpole, so it is going to expand, and that expansion will account for its change in volume. It will expand linearly. It will expand in terms of area. What we really need is to find the expansion in terms of volume. Now, in terms of volume, our expansion is 3 alpha initial volume times the change in temperature. The 3 alpha is the volume coefficient of expansion, 3 times the linear coefficient. So we need these values. So I need to know the volume of this flagpole. I was only given the length, 100 meters, but I was given the mass, and I was given the density of aluminum, so I can find the original volume that way. In other words, since density equals mass per volume, then the volume of this flagpole should equal the mass divided by the density. And so if I take 8,000 kilograms divided by 2.7 times 10 to the 3, 2,700 kilograms per meter cubed, that would be the volume of this flagpole. And that comes out to 2.96 cubic meters. So that is the initial volume of this flagpole, and that's what's going to go in here. Now I can find my change in volume. That's going to be 3 alpha initial volume times change in temperature, 3 times 24 times 10 to the minus 6 times 2.96 times 10 degrees Celsius. And if I put all those numbers in, I get 2.13 times 10 to the minus 3 cubic meters. That's how much this flagpole expands. Just a little bit more than 2 liters for this flagpole. So the work done by the aluminum will be the pressure times the change in volume. The pressure is the ambient pressure around the flagpole. That is the 1 atmosphere. But we want that in the SI system, so that's going to be 1.013 times 10 to the 5 newtons per meter squared times the volume, change in volume, 2.13 times 10 minus 3 meters cubed. This will give me Newton meters or joules, and that comes out to 215.9 Newton meters or joules. So the work done by the flagpole is 215.9 joules. Note that this data, the flagpole being 100 meters long to begin with, is extraneous information. It was not needed. We didn't need it to figure out the volume. And in fact, it probably would lead you astray because you probably would think this was a linear expansion rather than the volume expansion, given that you're given the L naught for that. So beware. Problem number 23. An 8,000 kilogram aluminum flagpole, 100 meters long, is heated by the sun from a temperature of 10 degrees Celsius to 20 degrees Celsius. Find the heat transferred in joules to the aluminum if the specific heat of aluminum is 0.215 calories per gram per degree Celsius. All right, so this is actually the same problem that we had in problem number 22, only now they're asking for the heat transfer, not the work done by the aluminum. And we're given that the specific heat for aluminum is 0.215 calories per gram per degree Celsius. We want this in the SI system, so we want this to be in terms of joules per kilogram. And there's 4.186 joules per calorie. And of course there's 1,000 grams per kilogram. So in other words, if I multiply this number, 0.215 times 4,186, I would convert into the SI system from calories per gram to joules per kilogram. And so 0.215 times 4,186 gives me a nice number, actually, 900 joules per kilogram per degree Celsius. That's our specific heat for aluminum. Now we want to find the heat transferred, and for heat transferred, that is the mass times the specific heat times the change in temperature. And in this case, for 8,000 kilogram flagpole, it's 8,000 times 900, 10 degrees Celsius, and that is 7.2 times 10 to the 7 joules. So a lot more heat transferred than on the order of almost 10 to the 8, a lot more than compared to the work. Problem number 24, an 8,000 kilogram aluminum flagpole, 100 meters high, is heated by the sun from a temperature of 10 degrees Celsius to 20 degrees Celsius. Find the increase in internal energy in joules of the aluminum, noting that the coefficient of linear expansion is 24 times 10 to the minus 6 per degree Celsius, and the density 2.7 times 10 to the 3 kilograms per cubic meter, and the specific heat is 0.215 calories per gram per degree Celsius. Problem number 24. Well, this is the same problem as 22 and 23. In those problems, they ask for the work done by the aluminum pole and the heat transferred to the pole, respectively. Now we're asking for the change in internal energy. By the first law of thermodynamics, the change in internal energy should equal the heat added to the system plus the work done on the system. The heat added to the system plus any work done on the system would be energy that was added to the system, and that would be the change in energy of the system. Well, we've already figured out these two things from the previous problems, 22 and 23. This was 7.2 times 10 to the 7 joules for the heat added. Now, on problem number 22, we figured out the work done by the system. The work done on the system is the negative of the work done by the system. So the work on the system is the negative of the work by the system, so this would be a negative 215.9 joules. So that's what we're going to put in there. So I have 7.2 times 10 to the 7 plus a negative 215.9. And so that means our change in internal energy for all practical purposes will still be 7.2 times 10 to the 7 joules. And because it's mostly the heat added to the system. Ready?
Good.
Problem number 25. 2 kilograms of water at 100 degrees Celsius is converted to steam at 1 atmosphere. Find the work done in joules. The density of steam at 100 degrees Celsius is 0.598 kilograms per cubic meter. 25. We're going to be looking at 2 kilograms of water at 100 degrees Celsius, and we wish to convert this to steam at 1 atmosphere. So we're going to keep the atmospheric pressure constant. P is constant. So this will be isobaric. If it's a constant, that means the work done will equal this constant pressure times the change in volume of our substance. Or our substance is actually going to go from water to steam. So it's going to go from a small volume to a very large volume. How do we figure out that volume? We can use that density equals mass per volume. So volume will equal mass divided by density. And so then the volume that we're going to start with is going to be the volume of the water itself. So the volume of the water, our initial volume, will be the mass of the water divided by the density of the water. And we're going to start with 2 kilograms. So we'll have 2 kilograms, and the density of water is 1,000 kilograms per cubic meter, at least if it's pure water. So this would be 0.002 cubic meters is our initial volume. Our final volume will be the volume of the steam. And that's going to be the mass of the steam divided by the density of the steam. We're still going to have 2 kilograms, but we're told that the density of steam is 0.598 kilograms per meter cubed. So this will give us 3.34 cubic meters. Much greater volume. So our work done, which is pressure times the change in volume, will be the pressure. This is all going to be done at 1 atmosphere. So we'll have 1.013 times 10 to the 5 pascals times final volume 3.34 minus initial volume 0.002. And this will be 3.37 times 10 to the 5 joules. So that's the work done in that conversion. Problem 26. 2 kilograms of water at 100 degrees Celsius is converted to steam at 1 atmosphere. Find the change in internal energy in joules. Note that the latent heat of vaporization for water is 2.26 times 10 to the 6 joules per kilogram. All right, so on this one, problem 26, we want the heat added so that we can use our result from the last problem to figure out the change in internal energy. So let's figure out the heat added for this phase change. And that's the phase change from water to vapor, from the water to the steam. And that'll be the mass times the latent heat of vaporization for water. We have 2 kilograms, and we're told that this latent heat of vaporization is 2.26 times 10 to the 6 joules per kilogram. So this will be 4.52 times 10 to the 6 joules. That's the heat involved in this phase change. We want to find the change in internal energy. So we want, by the first law, the change in internal energy will equal the heat added plus the work done on the system. This will be 4.52 times 10 to the 6. Now we figured out the work done by the system on the last problem. So the work done on the system is going to be the negative of that result. So we have a negative 3.37 times 10 to the 5. That would be the work done on the system. And when I add these two, I get 4.18 times 10 to the 6 joules. So that is the change in internal energy of this system. Problem number 27. How much heat in joules is required to convert 1 kilogram of ice at 0 degrees centigrade into steam at 100 degrees centigrade? The latent heat of ice is 333 joules per gram. The latent heat of steam is 2.26 times 10 to the 3 joules per gram. Well, we're going to start with some ice. And it's at 0 degrees Celsius, 0 degrees centigrade. And we need to first convert this ice into water. So that's going to require some amount of heat. We're going to have to go through a phase change between the solid and the liquid. And so that heat for that phase change is the mass times latent heat of fusion for the water. Since we have 1 kilogram, this is going to be equal to 1 times 333 joules per gram times 1,000 grams per kilogram. So this will be 3.33 times 10 to the 5 joules required to convert 1 kilogram of ice into water at 0 degrees centigrade. Now we have to heat that 0 degrees centigrade water up to 100 degrees centigrade water. So we're going to have water, and this heat required to do that will be the mass of the water times the specific heat of water times the change in temperature. And we're going to have 1 kilogram. The specific heat is 4,186 joules per kilogram, and our change in temperature is going to be 100 degrees Celsius minus 0 degrees Celsius. So this comes out to 4.186 times 10 to the 5 joules. That would be the heat required to bring 0 degree water up to 100 degrees water, just temperature change, nothing else. Next, we want to convert this water into steam. So we're going to go through another phase change. We're going to have heat required for that. Let's call this Q1, Q2, and Q3. Heat required for that is going to be the phase change, mass times latent heat of vaporization. So that's going to be 1 kilogram times 2.26 times 10 to the 3 joules per gram. But 1 kilogram is 1,000 grams per kilogram. So this is going to be 2.26 times 10 to the 6 joules required for that conversion. So now we'll have steam at 100 degrees Celsius, centigrade. Went from ice to water to steam, and the total heat required is all three of these heats. And can I fit it in at the bottom here? Let's go. All three of these add together. Would be 0.333 plus 0.4186 plus 2.26, all this times 10 to the 6. And that is 3.01 times 10 to the 6 joules. That's the heat. Most of the heat required, more than 2/3 of it, is the heat required to actually change it from hot water into steam. Problem number 28. A gas expands from A to B, as shown in the graph. Calculate the work in joules done by the gas. 1 atmosphere is equal to 1.01 times 10 to the 5 newtons per meter squared. Well, we're given a graph. This is problem number 28. And it's really a PV diagram. We've got pressure on the y-axis and volume on the x-axis. And see, up here is 6, here's 2, this is 2, and this is 8. There's our 2 points, and there's our line right there. So the gas is going to expand to a greater volume. It's going to go from 2 meters cubed to 8 meters cubed. As it expands, it's going to lose pressure, but this is an expansion, so work is going to be done by this gas. And the work done by this gas, the work done by any plot on a PV diagram is indeed the area underneath that plot. So this would be the work done by the gas. So if I can calculate what that area is, that would be the work done by this gas. So really that area is the area of two things. I got this triangle here. And I also have this rectangle. So let's just figure out the area of those two things. Now the area of the triangle will be 1/2 the base times the height. And so that would be 1/2. Now my base will be 8 minus 2. It would be the length of this right here. So that would be 8 minus 2, so 6 cubic meters. And my height will be 6 minus 2, so that's 4. So that's going to be 2 times 6 or 12. And the units of this will be atmospheres, meters cubed. Deal with that later in a moment. But we have 12 for the area of that triangle, 12 atmospheres meters cubed. the area of the rectangle would just be the base times the height. That's the area of this right here. That's going to be 6 times 2, or 12 atmospheres meter cubed. So our total area will be the sum of these two areas, the area for the triangle and the area for the rectangle. That's going to be 12 plus 12, or 24 atmospheres meters cubed. We probably want to put this in terms of joules. We want this in terms of work, which is energy. So let's convert atmospheres to the SI system. And so we'll say that the work we're looking at, which is 24 atmospheres meters cubed, will be 24 times conversion of 1.013 times 10 to the 5 newtons per meter squared, that's 1 atmosphere, times meters cubed. So 24 times that gives us 2.43 times 10 to the 5 joules. So the work done by this gas will be 2.43 times 10 to the 5 joules. Problem number 29. A gas expands as shown in the graph. If the heat taken in during this process is 1.02 times 10 to the 6 joules, and 1 atmosphere is 1.01 times 10 to the 5 newtons per meter squared, the change in internal energy of the gas is, in joules, what? Well, let's start here. It's the same problem as the previous one, the same graph at least. And we're told that the heat taken in during this process is 1.02 times 10 to the 6 joules. So our heat added is this. And it's the same graph, so we can say that the work done by the system was this total right up here. That's the work by, but the work on the system will be the negative of that. So work is negative of work by. That's going to be negative 2.43 times 10 to the 5 joules. But we were asked that should be times 10 to the 6. I'm sorry. I want to change on the previous one. 24 times all that will give you times 10 to the 6. And this would be times 10 to the 6 as well.
Okay.
All right. Just take a note of it. Hopefully you watch these in progression. So, by the first law, change in internal energy is the heat added to the system plus the work done on the system. And that will be 1.02 times 10 to the 6 plus a negative 2.43 times 10 to the 6. That'll give us a negative 1.41 times 10 to the 6 joules. So even though heat was added to this gas, it actually did more work than the heat that was added. So actually the gas lost energy, internal energy, in that expansion. Problem number 30. The Earth intercepts 1.27 times 10 to the 17 watts of radiant energy from the Sun. Suppose the Earth, a volume 1.08 times 10 to the 21 cubic meters, was composed of water. How long would it take for the Earth at 0 degrees centigrade to reach 100 degrees centigrade if none of the energy was radiated or reflected back out into space? Here's problem number 30. We're told that the Earth intercepts 1.27 times 10 to the 17 watts of radiant energy from the Sun. Well, let's find the total energy needed first of all, to raise the temperature of a Earth that is totally comprised of water from 0 degrees centigrade to 100 degrees centigrade. So we're going to have this Earth totally full of H2O. And we wish to change temperature from 0 degrees centigrade to 100 degrees centigrade. So the amount of heat required to do that would be the mass of the Earth times the specific heat of water times the change in temperature. Now we can't use the normal mass of the Earth, which is 6 times 10 to the 24 kilograms, because that's the mass of the Earth as rock and so forth. We're told that this Earth is made out of water. So we're going to use that the mass of the Earth is the density of water times the volume of the Earth. And we were given the volume of the Earth in this problem. So this would be 1,000 kilograms per meter cubed, and the volume given for the Earth was 1.08 times 10 to the 21 cubic meters. So this is going to be 1.08 times 10 to the 24 kilograms. So if the Earth is comprised of water, it'll be about 1/6 as much the mass than the true Earth. Well, this is what we're going to put into there. So this is kind of like a sidelight thing. So now our heat is going to be the mass, which is 1.08 times 10 to the 24 times the specific heat of water, which is 4,186 joules per kilogram, times the change in temperature, which will be 100 minus 0. And this will give me 4.52 times 10 to the 29 joules. That's how much energy would be required to change the temperature of the Earth from 0 to 100. But the question was, how long will it take to get this much energy in order to heat up the Earth based on how much energy we currently get from the sun? And we're told the Earth intercepts 1.27 times 10 to the 17 watts of that energy right now. When we talk about that, that's power. In other words, the power we intercept from the sun is this. A watt is a joule per second. And power itself is energy per time. Represents energy per time. So, if we want time, that would be energy divided by power. So we would take this energy, divide by that power, and that would tell us how much time it would take to create this heating. And that's going to be 4.52 times 10 to the 29 joules, divided by 1.27 times 10 to the 17 joules per second. And this will be the time in terms of seconds. That's going to be 3.56 times 10 to the 12 seconds. It's required. Now, none of the answers are in seconds, so we need to put this into years. So let's convert. We know that there is pi. Let's see, there's 1 year per 3.16 times 10 to the 7 seconds. I usually say pi times 10 to the 7 seconds for a year, but it's really, if we want to be more exact, 3.16. I'm not sure if I use that in these numbers here. Seconds cancel out, and I get 1.13 times 10 to the 5 years. So in order for the Earth to heat up so that the water comes to a boil, it will take 100,000 years. Problem number 31. Beryl states that insulation with the smallest possible thermal conductivity is best to keep a house warm in winter, but worse for keeping the house cool in summer. Sapphire insists the reverse is true. Low thermal conductivity is good in the summer but bad in the winter. Which one, if either, is correct?
Ready.
So Barrow's saying that if you have insulation with the smallest possible thermal conductivity to keep a house warm in winter but worse for keeping a house cool in summer, Sapphire insists the reverse isn't true. Well, really what you want is insulation that has low thermal conductivity so that it insulates from exchange of energy between the inside and the outside. In either case, I mean, if it's in the summertime, you don't want warm air coming in, and if it's wintertime, you don't want warm air going out. So you want to limit the exchange in either case. So you want high low thermal conductivity in either case. So Barrow's not correct, Sapphire's not correct. Diamond should be correct, because she says that it's neither, because low heat transfer is desirable both in summer and winter. So we'll take the gemstone Diamond on, take her word for it on this one. Problem number 32. A 100 kilogram marble slab falls off a skyscraper and falls 200 meters to the ground without hitting anyone. Its fall stops within milliseconds, so that there's no loss of thermal energy to the surroundings if its temperature is measured immediately after it stops. By how much has the temperature changed as a result of the fall if we ignore energy gained or lost as a result of its interaction with the atmosphere? All right, so we have, let's say we have some kind of building, and we drop a marble slab from the top of this building. The mass of this is 100 kilograms. And it's going to fall 200 meters to the ground. So this height is 200 meters. So we have all this potential energy that's going to go into kinetic energy as it's falling. And we're told that we're not going to have any losses to friction or anything else. And it's going to hit the ground. And all that potential energy will eventually go into thermal energy, heating up the marble. So let's figure out how much energy that is. Potential energy is just mgh from mechanics. And that's going to be 100 kilograms times 9.8 times 200 meters. This will give us the energy, which turns out to be 1.96 times 10 to the 5 joules. That's how much energy we need to now distribute in the marble slab, and as a result of that, the marble slab is going to increase in temperature. So all this will go into heat. All this will go into heat of this form, mass times specific heat of the marble times its change in temperature. That means that the change in temperature of the marble will equal the heat divided by the mass divided by the specific heat of marble. And this will be 1.96 times 10 to the 5 joules. The mass of this marble slab was 100 kilograms. And the specific heat of marble was given in the problem. I didn't state it when I read it. The specific heat of marble is 860 joules per kilogram per degree Celsius. So that's 860 right there. And that gives me 2.28 degrees Celsius. So when this marble hits, ignoring all other losses, it will gain in temperature by 2.28 degrees Celsius. Problem number 33. The specific heat of an ideal gas at constant pressure is greater than the specific heat of an ideal gas at constant volume because what if you have a gas at constant volume, if the volume can't change, if it's constant, then you can't do any work. So all of your, there's no work done, there's only heat added. Whereas for a gas at constant pressure, you can do work. You can, the gas can expand, is allowed to do work, hence it can do more, and so the specific heat has to be greater than that of one at constant volume.
Good.
Problem number 34. 100 grams of liquid nitrogen at 77 K is stirred into a beaker containing 200 grams of 5° centigrade water. If the nitrogen leaves the solution as soon as it turns to gas, how much water freezes? The heat of evaporation of nitrogen is 6.09 calories per gram, and the heat of fusion of water is 80 calories per gram. All right, so we're going to add 100 grams of liquid nitrogen to some water. That's 200 grams of water at 5° centigrade. Now, what we need to know is when we lose all this nitrogen, it's going to actually cool the water. We need to know how much energy is going to be gained by the nitrogen, and then that will be the energy that will be lost by the water. So we're basically going to say, for problem 34, that the heat gain by the nitrogen will equal the heat lost by the water. So let's, heat gained by the nitrogen will equal the heat lost by the water. So let's figure out the heat gained by the nitrogen first as we vaporize this nitrogen. Well, we would say that for the nitrogen, that the heat will be equal to the mass of the nitrogen times latent heat of vaporization for nitrogen. And we're going to have 100 grams. And we're told that latent heat for vaporization nitrogen is 6.09 calories per gram. So this is going to be 609 calories. We can change that to joules, but let's just keep it in calories for now. Let's see how much energy we need in order to cool water from 5° centigrade down to 0° centigrade. And then, if we have any energy left over, then how much energy we have left over in order to turn that water into ice, and then see how much ice we can make. So first thing we have to do is cool all the water down to 0, and then whatever's left over will convert some of the water into ice. Well, the energy needed to cool water from 5° centigrade down to 0° centigrade would be equal to the mass of the water times the specific heat of water times the change in temperature. And that energy for 200 grams would be 200 times 1 times 5 minus 0. And that will be 1,000 calories. So it would take, we would have to remove 1,000 calories from the water in order to change it from 5° centigrade down to 0° centigrade. But we only have 609 calories available. So the water will never cool down to 0. It won't even make it to 0. And if the water never cools to 0, then none of it will change to ice. So none of the water. So we don't even have to worry about the phase change, because they'll never make it there. 35. A styrofoam container used as a picnic cooler contains a block of ice at 0° centigrade. If 225 grams of ice melts in 1 hour, how much heat energy per second is passing through the walls of the container? The heat of fusion of ice is 3.33 times 10 to the 5 joules per kilogram. All right, so on this problem we have a styrofoam container, it's a picnic cooler. It's holding a block of ice. We found that 225 grams of ice melted in 1 hour. So let's figure out how much energy that is that it took to melt 225 grams of ice. Well, the energy would equal the mass of the ice times the latent heat of fusion. And we melted 225 grams of that, which would be 0.225 kilograms. And we're given the latent heat of fusion for water is 3.33 times 10 to the 5 joules per kilogram. So this is 74,925 joules. That represents the heat lost in 1 hour, because we ended up melting that much ice. So that we must have lost, or the heat gained to the ice in 1 hour. So that's how much transfer is taking place in that 1 hour. And we wanted to find how much heat energy per second is passing through the walls of the container. So we have that the heat per hour is this. It would be this much per 1 hour. We probably want that in terms of per second. So we'll say that there is 1 hour for 3,600 seconds. And so we have 74,925 divided by 3,600 gives us 20.8 joules per second, or 20.8 watts. So that's how much energy per second is passing through the walls of the container.
Okay.
Problem number 36. In braking an automobile, the friction between the brake drums and the brake shoes converts the car's kinetic energy into heat. If a 1,500 kilogram automobile traveling at 30 meters per second brakes to a halt, how much does the temperature rise in each of the 4 8-kilogram brake drums? The specific heat of each iron brake drum is 448 joules per kilogram per degree Celsius. All right, so in this problem, we're going to stop a car, a speeding car, at 30 meters per second, which would be about 67 miles per hour or so. And all that energy, all that kinetic energy of the car is going to be transferred to the brake drums, the 4 brake drums. So let's figure out how much energy that is first. Our change in kinetic energy is going to equal our, well, at least in magnitude, our magnitude of our final kinetic energy minus our initial kinetic energy. Our final is going to be 0. So the magnitude of this is going to at least equal the initial kinetic energy. And that is going to be 1/2 the mass times the initial velocity squared. That'll be 1/2 times is a 1,500 kilogram automobile moving at 30 meters per second. And this amount of energy is 675,000 joules. That's going to be transferred to the brake drums as the brakes are trying to stop the car. They're trying to dissipate this much energy in the process. But we have 4 brake drums, hopefully, 4 operational brake drums. So each drum will have to deal with 1/4 of this. So we'll say that the heat that we're talking about for each drum is going to be this total energy divided by 4. This is for each drum. And so that will be 168,750 joules. So each drum will have to deal with that much energy. And as a result of trying to dissipate that, the drums will heat up. So this heat will also equal the mass times the specific heat times the change in temperature of the drum. And so our change in temperature will equal the heat divided by the mass times the specific heat for the drum. This would be 168,750 joules divided by the mass of the drum, 8 kilograms. And we're told that the specific heat of the drum is 448 joules per kilogram per degree Celsius. So that gives us 47.08 degrees Celsius. So each drum will increase by 47 degrees Celsius, which is a lot, because each degree Celsius is 9/5 of a degrees Fahrenheit, almost 2 degrees Fahrenheit. So we're talking about 9 degrees Fahrenheit. So that